Fortunately, everything is recorded here at the BHI, and I will be able to catch up, although not ask Pawan questions. We are delighted to have Pawan Kumar with us today, a old friend, and that has perhaps the most appealing model for fast radio bursts, a very puzzling phenomenon, as you will hear in a few minutes. I just wanted to say that the conference is 3 weeks away, so if anyone forgot to register, this is the time. There is also a banquet where we will hear Clifford Will talk about the history of black holes over the past century. So it should be a fun event on Monday night, the 8th of May, and then we have 2 days of the conference. You can see the program on the BHI website. And one other announcement, the Event Horizon Telescope successfully completed 5 full days of data collection. Very successful, the weather was great, the data was great, and we look forward to hearing the analysis results, hopefully within the coming months.
Me too.
Yeah, that includes you, but which we are all rooting behind for your success. So hopefully we'll get better image or sense of an image. Do you think a real image of the shadow?
We like to under-promise and over-deliver. So we'll see what we see.
What is your under-promise then?
We think we have some good data, and let's see what happens.
Okay.
That's not a promise, that's a statement of fact.
We will analyze this promising data.
And hopefully see a shadow. That's what we all hope. And without further ado, let James introduce Pawan.
Thank you. Have a good trip. I just want to make sure that since it's being recorded, anything that I say will be used against me.
No, in favor.
Be very careful. Have a good trip.
Thank you.
So today we're delighted to have 1-2 punch of Pawan Kumar and student Wenbin. So when I Googled actually your name, I come up with an Indian wrestler as the first hit. So I don't know.
You can look at me.
So just be careful with your questions and don't go over time because you'll be tired. Pawan will be talking about fast radio bursts, which has done lots of great work on repeating systems, GRBs, and tidal interactions. And Wenbin will be talking about tidal disruption events afterwards, specifically the jetted 1644 event. They had a paper on testing for the whether black holes have a hard boundary, which was quite an interesting proposal, which is predicated on the rate of observed tidal disruption events. So they've been doing really exciting work, and so we're happy to have them speak today. Oh yes, pizza at 4:30. So stick around if you want to get free food and to chat more science with your colleagues.
Thank you very much. The audience, I had actually had not quite realized that the audience is going to be so mixed, which is to say mathematicians, physicists, not just astronomers, philosophers. And I had actually prepared it with the misconception that this is going to be primarily an astronomy, astrophysics audience. I will try to kind of adjust my talk so that I hope that at least the mystery of this thing can be communicated to every single one of you, but that's at least would be the goal. But I also want to communicate certain technical aspects of things about the model that those of you who work in astrophysics can judge by yourself the validity of the model or the merit of the model. So with that, what these things are, these fast radio bursts are events that are seen lasting for a short period of time, millisecond, roughly about a millisecond, very bright, and the first one was detected in 2007.
This won't work on the screen.
It will
Use your
not work.
hand. Just
Okay, that's fine.
it's like a black hole.
Okay,
Yeah.
that's fine. So these things, what you see here is that the arrival time is frequency dependent, the pulses, the short duration pulses, arrive earlier at high frequencies, and then there is a delay. The x-axis here is time in milliseconds. This is the frequency axis. I will just read it to you in case you cannot see it from the back of the room. This is frequency in gigahertz. So these things are seen at frequency of gigahertz. This is 1.5 gigahertz to about 1.2 gigahertz, and there is a delay. And that is what the surveys, these radio surveys, were designed to look for this large delays or high, what astronomers call dispersive measure. These things have very high dispersive measure, meaning large delay, which means high column density of electrons between us and the source. The work that I describe here is being done mostly with Wenbin and my another graduate student, Mukul. So with that, the next few slides is a quick rundown and provides an overview of the observations of these objects. And then I go into talking about what are these objects and how the radiation we see is produced. That's where we are going. Well, that's where I'm going. The duration of these things is typically a millisecond. You see a big spike. Oh, I keep forgetting that it will not. So there's a big spike here. So large fraction of these events are seen about a millisecond. But there is a tail. There are events lasting for as long as about 20 milliseconds. But the typical time, as I say, is a couple of milliseconds, short duration events in the gigahertz radio band. One of the events, so the 17 have been detected. One of these 17 events was seen to repeat many times. In the last 4 years, it has been seen to repeat about 150 times. 17 of these times, papers have been published reporting the observation of 17 of these repeat. And that's shown here in this particular figure. The main point is to show that the duration coming from the same object is not always the same. There is a distribution.
I'm sorry, on the previous slide, it looked like there were maybe about 15 total events, but now you're saying there's a lot.
There's one of those 15 events. You're looking at one of those 15, and that particular object is undergoing repeated bursts. It has gone many bursts, and this data that you see here is 17 of about 150 that people have recorded in the last 4 years. Yeah, so that's the difference between the two. And the same object is producing outbursts lasting from anywhere from a millisecond to, in this case, you can see 10 milliseconds. But there seems to be a rapid drop here in the terms of the duration. So maybe that this particular object is not going to produce outbursts lasting for 20 milliseconds. Seems data, the 150 burst data will be coming out sometime, and we would have a little more information. But anyway, based on this, that's what we have. This slide now provides the summary of the observational data, and then I will get into what these objects are. So the summary of this is straightforward. The duration is, typical duration is a millisecond, some less, some more. Dispersive measure, if you know, that's fine. If you don't, doesn't matter. It simply is a measure of, roughly speaking, a measure of the distance to these objects. It's something on the order of dm is 1,000. Distance-wise, in one case we know the distance very precisely, about a gigaparsec. These other ones are probably similar. Distance is gigaparsec, meaning about 3 billion light years. The distribution is most likely isotropic. Certainly it is consistent with an isotropic distribution in the sky. There is no particular preference for which direction they are coming from. The best that we can tell, although this is slightly debated, and there are selection effects. The amount of energy that is released, if these things were to be isotropically radiating energy in the explosion, is something on the order of 10 to the power 39 picogram, which is, by astronomical standards, is very small. but it's very large amount of energy coming out in the radio band in a millisecond. So that's a very powerful source in the radio. If it were to come out in the X-ray, just to give you a perspective, those of you who are outside of astronomy, that will be nothing to write home about. Absolutely nothing.
How do you know what the energy is? Because it depends on the distance.
Very much so. So in one case, we do know the distance. In other cases, we do not know the distance, but we know the number of electrons per unit area between us and the source. And from the knowledge of, or making a rough estimate of the number density of electrons, we can estimate the distance. That's what people do, or have done. That's how we do. That's all I'm going to say really about observations. And now the remainder of about 22 minutes that I have, 20 minutes I have, is going to be devoted to telling you what these things are. And I'm going to tell you the bottom line first, what they are, and then fill in the details, give you arguments as to why I think what these things are and how they are producing the radio. So I will give you that summary up front and then provide the details. Yeah. So there are many possibilities here. This is only a partial list. You see the dot. There are 17 observed. The number of possibilities that people have discussed, I think, is more than 17. Okay. Including things like it could be accreting black holes. It could be. I think it's unlikely, but that's a possibility that people have entertained. Yeah. So I'm just listing. I'm telling you many different possibilities. With that, what I'm going to tell you is a summary of what is going on, and then provide some arguments to justify this result that I'm going to tell you. So the bottom line is that these things are produced by a neutron star, which is highly magnetized, with magnetic field strength of 10 to the power 14 Gauss or more, so-called magnetars, strength magnetic field. The radiation is produced by electrons being accelerated by various intense electric field and following magnetic field lines, or the curvature of magnetic field lines. Accelerating electrons radiate, and if electrons are moving in the same direction, meaning in phase, and having acceleration vector also lined up, then the electric field of the radiation they produce is going to act coherently. And therefore, the radiation that comes out goes as number of particles squared, and that provides a powerful radiation, and that's called antenna. That's how the radio antennas work. And so that's the mechanism that seems the most likely to be able to explain the data and the variety of constant that we have got. So I have told you what it is. If you wish that this is what all you wanted to know and you want to leave, of course, by all means, you should feel free to. You would not be offending me. Rest of the talk is simply going to tell you why we have arrived at this particular result. Okay? So with that, sorry, you want to leave?
No, no, I said I want the details.
You have asked for it then.
Yeah, right.
But coming back, serious, I have, the time is very limited and I do not want to cut the time from the next speaker. So I have to be very efficient in the conveying the information. One thing, again, slightly technical for those of you who are not working in astrophysics, is from the radiation that we see, we can ask what should be the temperature of the object if the object were to radiate like a black body. That astronomers call the brightness temperature. The brightness temperature, you can calculate, is a straightforward thing to do, turns out to be very high. 10 to the power 35 Kelvin. That is completely unphysical for a wide variety of reasons. No time for me to go into it. So please accept it. If you have got a question, you can always ask me at any point, now or later on. Completely unphysical. So that suggests this object is radiating not in an incoherent way, but photons are being produced coherently, where things are superposing in phase. That's what this is telling you. And there are three broad category of mechanisms that can do the job. And they are listed here. Maser. I don't need to tell any of you what maser is. So that's a mechanism. The bottom line for the maser is that what you have is that photons, even a random photon could be traveling through a medium, and it gets amplified because it stimulates particles to radiate, which means in the language that astrophysicists use, it has a negative, the medium has a negative absorption coefficient. That's what it means. You could have other process where you have a kinetic energy in a beam of particles that gets converted to plasma waves, high amplitude plasma wave, and then you convert the energy from the plasma wave to photons, to gigahertz photons that we see. That's another class of mechanism. The third I have already alluded to in my bottom line, antenna, where electrons are all moving in roughly the same direction. The velocity vector is almost parallel, and so is the acceleration vector, almost parallel. So the electric fields add up coherently. Superposition is additive as opposed to cancelling out. So that's the third class of mechanism. Those are the possibilities. That's it. There is not a fourth class of possibilities. What I'm going to do in the next 5 minutes is to tell you that these two class of mechanisms doesn't seem to work. It runs into a big problem. And then show you that this seems to fit the observations. That's where I'm going. These two class of mechanisms produce radiation at a frequency which is closely related to plasma frequency. Okay, so that's the part that I will be making use of. Here is providing the constant on these first two class of mechanisms, and the basic idea is that you have got particles which are accelerated, attain a certain energy and a certain luminosity, and you convert the kinetic energy of this beam of particles to radiation. That's in the end what these two classes of mechanisms are doing. So you can put some constant, assuming that the object is compact like a neutron star or a black hole. What you could do is provide the constant on the magnetic field or the distance from the surface of a neutron star, where these particles being this outflow of kinetic energy would be generated, and it's just a purely energy argument. Simply saying how much energy is available, and that energy available, the energy density available, is the magnetic field strength squared times the radius at which this thing is being launched at times the speed of light. That's the maximum luminosity you can hope to get from this object. Putting those numbers, what you find is that luminosity is huge, 10 to the power 49 ergs per second, if the magnetic field strength is 10 to the power 14 Gauss. If you do it at the surface of the neutron star, the radius of which is about 10 kilometers, you can get very large amount of energy, and that cannot come by trying to spin down the neutron star. That time scale is much too long, and the amount of the luminosity that comes out is much too small to explain the luminosity of these fast radio particles. So what you need to do is convert the energy in the magnetic field to energy in the particle by some very fast process. Let's not worry what it does, but something is doing that, yeah? And then what you need to do is the following, that a fraction of this luminosity, which L beam luminosity, is converted to gigahertz radiation. So clearly, if you are starting with kinetic energy in particles and then converting that to gigahertz radiation, the luminosity in the gigahertz radiation is going to be smaller than the kinetic energy luminosity in the beam. So you put that thing here, and the kinetic energy, the radioluminosity is 6 orders of magnitude smaller. So that puts a constraint on the radius, the maximum radius at which you can launch this jet, this outflow of particles, to be able to produce this luminosity we see in the gigahertz. And that turns out to be something on the order of about 100 kilometers from the neutron star. You can't launch this thing at a distance larger than about 100 kilometers from the surface of the neutron star. It got to be there. But there is a second thing, and that is the following: that the energy ultimately has to be converted from the particle kinetic energy to the radio photons. And here's the thing: the energy carried by this particle beam is related to how fast the particles are moving, or the Lorentz factor of the particle, which is gamma, mass of the particle, c, speed of light, r is the distance from the object, and e, the density of electrons. So that's the luminosity that is carried by this outflow of particles, most likely electrons and positrons. But it need not be electrons and positrons, it could be electrons and protons. It doesn't matter for this particular calculation and this particular constant that I'm providing. But that's the luminosity that is carried by the beam. Here is the thing: the beam, the radiation that is produced by these two mechanisms, these two class of mechanisms that I mentioned, is producing radiation at a frequency which is close to or connected with the plasma frequency. Nu sub p from now on that I will be using. So that nu p in turn is related to the electron density. It goes as the square root of the electron density. So now what you could do is put things together. And what you find is that in order we can eliminate Ne from here using the frequency being the plasma frequency. And what you find is that the radiation can be converted from the kinetic energy to gigahertz photons at a much larger distance. So the beam needs to travel from 100 kilometers to a much larger distance and then dump its energy or convert its energy into gigahertz photons. Yeah? So, but that's not a problem. That's just what is needed. The problem is on the next slide, and that is this. You can do that, but it also tells you that you need to produce, the plasma frequency is a gigahertz or closely related to it, and you have the luminosity, which gives you the total number of particles, and that total number of electrons that you need to produce the gigahertz photon that we see in these bars needs to be greater than 10 to the power 41 number of electrons or positrons. And that's a big problem for the following reason. The total number of electrons and positrons in the magnetosphere of a magnetar is 9 orders of magnitude smaller. So you clean the entire magnetosphere of the neutron star and still you fall short by 9 orders of magnitude. In other words, you don't have enough particles to be able to produce the emission that we see. That is the problem. There are ways people talk about that maybe you can increase the number of particles, but this factor is so large that it's not possible. Again, you can ask me later on why, but it's not possible to produce 1 billion times more electron positrons than they are likely there in the magnetosphere. Okay, so that's the big problem, and that, in my opinion, kills the two classes of mechanisms that I mentioned here. And that leaves us with this third possibility, and that is our model that we have. And here's the way it works. You have electrons which are moving at a speed close to the speed of light with certain Lorentz factor gamma, and they are following magnetic field lines. The magnetic field is strong. 10 to the 14 Gauss means that particles have no choice but to follow the magnetic field lines. The gyro radius is absolutely tiny. And so these particles are flowing, and as long as the field lines are nearly parallel, just nearly parallel to within an angle of 1 over gamma, then they have the same velocity vector, nearly the same velocity vector, and they all have nearly the same acceleration vector. So the electric field produced by the acceleration of these charged particles will add up coherently, and it will lead to this coherent curvature radiation. That's the idea. And the frequency can be calculated. Completely straightforward way to calculate what the frequency of the radiation coming out will be, what the luminosity will be. Again, very straightforward thing to do. I just want to draw your attention to the fact that the luminosity goes as the electron number density squared. And the electron number density that you need is 10 to the power 16 centimeter. The total number of electrons that you need is 10 to the power 30 electrons, not 10 to the power 41 electrons. Okay, so and that is totally manageable. It's a small fraction of the electrons and positrons in the magnetosphere of the magnetar. So this thing is the scenario, but some more information. You have electrons which are moving in the same direction, therefore you have a current, and the current is huge current because you have got large number of electrons all moving parallel. So this large current flowing in this direction will also induce a field which is going to be perpendicular to this original magnetic field. You can calculate the strength of that field is 10 to the power 12 Gauss. What that will do, if the original field were to be weaker than this thing, is the following: that it will modify the field direction. The fields will be torqued. You will have a torsion induced in the field, and electron acceleration vector will no longer be parallel. So the only way we can maintain the coherence and make sure that all electrons are radiating in phase is to ensure that this induced magnetic field doesn't provide large torsion to the original magnetic field. And for that, the original magnetic field must be greater than 10 to the power 14 Gauss to ensure that this induced field of 10 to the power 12 Gauss doesn't cause electrons to become out of phase, acceleration wise. So that's where this strong field is coming from. With that, we have other consideration. These electrons are radiating. The Lorentz factor is 30. They will lose energy on a very, very short time scale. 10 to the power 15 seconds is all it takes for the electron to lose its energy, and they will stop radiating. The radiation lasts, to remind you, for a millisecond, which is 12 orders of magnitude larger than the cooling time. So the only way you can maintain the electrons and have them radiate is by providing a mechanism to keep electrons accelerated, and for that you need electric field. So you need a strong electric field to keep the electrons, maintain them at the Lorentz factor of 30. And that requires a strong electric field of 10 to the power 11 ESU in the CGS units. And that field is much, much stronger than what you have got even at the polar gap in magnetars. So this is a field that you need to make things work. And the way that you can, yes, go ahead.
You're talking about coherent radiation. So
Yes.
all these electrons are doing the same thing. How similar should that Lorentz factors be?
Within the Lorentz, the direction should be within one
Direction
over
should be very good. Yeah.
But the Lorentz factor could vary by a factor of a few, and you're fine,
And you're still
and you're absolutely okay.
okay.
So
Are there similarly limits on the organization of the magnetic
very
field?
much so. The magnetic field also needs to be nearly parallel to within an angle of 1 over gamma. But the region of space that we are talking about a region of space which is about 10 meters across. So you need parallel magnetic field in this small region of 10 meters across. Yeah, the size of the neutron star is 10 kilometers. Yeah, so it is really not asking for much. Yeah. So here is the way that you can generate this strong field. The only way that we know to generate a strong field and quickly is by reconnection. You have magnetic field lines, geometry, which are pulled together and reorganize magnetic fields and produce in that process a current sheet and a strong electric field. And this could come by in two different ways. One is that the surface of the neutron star, if it is young star, may not be completely settled. Things may be still moving around, distorting the magnetic field above the surface of the neutron star to a point where things become unstable and they reconnect. Yeah. The other possibility is that magnetic field lines may be emerged from below the surface of the neutron star and giving rise to the reconnection. These are the two possibilities that come to mind in a natural way. There may be other possibilities too. So this cartoon sketch is simply saying that magnetic field lines are forced to come together, reconnect, reconfigure, and produce this strong electric field. And you can calculate in this process how much energy is going to be produced in this process of reconnection. And this equation, those of you who know, simply saying how much energy Pointing flux is flowing into the current sheet, and that turns out to be sufficient, more than sufficient, to explain the energy requirement of the FRB. So there is plenty energy that is available here. The rest of the slide simply is telling you, or telling us, that the amount of energy in the magnetic field is 10 to the power 45. The amount of energy that is released in one of these bursts when you correct for the beaming is 10 to the power 36. So you have, certainly you can produce billion of these bursts. There is not a problem to have burst repeat many times. And in one burst, as I mentioned already, and I'm repeating, burst is seen to repeat maybe roughly once an hour. And not a problem. That is totally doable. This thing here is simply to tell you how little of matter is involved in these powerful explosions in the radio band. All that you need is 10 to the power 30 electrons that are positrons, so that what a kilogram of matter. A kilogram of matter is producing radiation that we see from a distance of several billion light years. So that's, well, I think impressive. With that, there is one technical issue, and I'm getting really to the last part of the talk, and I'm keeping track of the time to make sure that I do not overstep my time limit, is issue to make sure that there is a coherent radiation. You need to have particles bunched into bunches of size of roughly the wavelength of the wave. Gigahertz means 30 centimeters. And this is simply showing you that there are instabilities, two-stream instability, and other instabilities in the current sheet that provide you. And this is simply a calculation of the two-stream instability. The fastest growing mode has got wavelength something on the order of few tenths of centimeter. So things do seem to be okay, but there are issues here which I will be happy to talk with you about. Not everything is absolutely absolutely on the solid footing here. The lifetime of the magnetar that needs to that goes through this phase of activity is between 100 years and 10 to the power 4 years for reasons which are outlined here, but I'm going to skip and simply draw to the prediction. The prediction of this model, if this model is correct, that we should see FRB-like phenomena at high frequencies, millimeter and optical. The reason being that the Lorentz factor of the electron accelerated in the current sheet is going to depend on the electric field strength square root. The reason for the square root is that there is a back reaction of the radiation on the electron acceleration. Balancing the two, you get that Lorentz factor is the square root of electric field inside of the current sheet. And the frequency of the radiation goes as electron Lorentz factor Q. So you should have a wide variation in the strength of the magnetic field and the strength of the electric field in the current sheet, giving you a broad band, not from the same object, but different objects will have different conditions, give you emission coming out at different frequencies. The luminosity will go as the frequency to the power 4/3. The event rate will go down in a conservative way as 1 over frequency to the power 2/3. These are some of the predictions of the model if this is correct. And future observations will either show us wrong or will provide support for it. Yeah. So time will tell. With that, I have the final slide providing the summary, and I guess no time left, so I'm just going to leave it at that and take questions at this point if you would like to. I'm certainly around here for the rest of the day and tomorrow. So
We have time for 1 or 2 questions. People have. Bastard, I'm sorry.
So you're suggesting that the length scale is the scale of this two-stream instability. So it's not the radius of the gyro radius in the field.
that's too large. The gyro radius.
It's not the radius of the neutron star, but it's.
No, both of those things are much larger. They are order of kilometers, tens of kilometers. This the current sheet that is produced by magnetic field undergoing reconnection is a much smaller length scale.
And then you also mentioned reconnection. So there, the reconnection, the length scale with the reconnection is again, that's like plasma diffusivity. So
Very, very
how does
true.
that relate to the two-stream clumps that
They
you're
are very closely related. Turns out that if you look, for the parameters that I mentioned to you, the plasma length scale, which is C over plasma frequency, is something on the order of a few centimeters, and the length scale for the current sheet is typically maybe 100 times this plasma length scale. Few tens. This is not something that we know with confidence, particularly not for the parameter of interest to us, where the field is so strong. Nobody has done any simulation anywhere, so we can't really rely on the simulations. And analytical work on the reconnection is just not there.
So you're envisioning this tiny little region kind of being infected along and emitting, which is how they last for a millisecond, even though it's a region that's 10 meters across or something, right?
That's right.
So I was just curious, in all the events, especially these long ones, do any of them show, say, multiple peaks or something like? Because like giant pulses from crowd are all these little nano shots, and
That's right.
I thought some of the fast radio bursts had, say, multiple peaks.
They do have a lot of structure.
So
These have structures limited only by the resolution of the telescope. People have seen the structure certainly at 10 microseconds, and possibly they may be present even at a smaller time scale.
But would you expect that for this single region moving along?
It's not a single region. That is the only part that I wish to correct there. It is not a single blob that is moving. It only travels a distance. So the size is few meters, 10 meters, but it moves the distance of maybe about few 100 meters, and then exits. And then you have got plasma continuously flowing into the current sheet. New blobs are being generated. So you have got a series of these blobs moving through the current sheet, producing radiation. Each of the blob basically is producing radiation lasting for something on the order of about a nanosecond.
Let's continue. Well, is it very quick?
Yeah.
Okay.
You mentioned 10 meters several times.
That's right.
Where
Where
is
is
10
coming
meters
from?
coming from?
Gamma times lambda.
You need to multiply the gamma.
That's right.
And it's because it's moving towards you?
It is moving, no, not because of that. In the transverse direction,
Yeah.
you see, the easiest way to see this thing is going in the co-moving frame of the electron. The frequency is smaller by factor of gamma, the wavelength is larger by factor of gamma, and so the transverse length scale in the co-moving frame is gamma times
So
lambda.
it is the wavelength in the co-moving.
Exactly right.
Okay.
That's where it's coming
I
from.
have a super quick question.
Fine.
So this mechanism, the directionality of it,
Yes.
how does it relate to the normal pulsed radiation you would expect from a pulsar?
From a pulsar. Pulsars, this one is probably being a little bit more, but there is not a dramatic difference probably between the two. This is
You'd
beam.
expect to see
This is
pulsars.
2 degree. This is the beam size is 2 degree in our model.
But I mean the direction. Would you expect to see pulses from these FRBs if
No,
you
you
were
will
close
not.
enough?
No, because the neutron star is rotating with a period of about 100 milliseconds. The duration of these pulses, the burst that you see, a couple of milliseconds. No pulses.
Okay. Let's continue discussion later with pizza at 4:30. Only so like you.
I take what I can get.
Okay, I'm gonna switch to something completely different from FRBs, which I call TDs, tidal disruption events. So this is, I have been working on TDs for about 2 years. Those are the collaborators that I have worked with in the past, including some professors in UT, University of Texas, and including Ramesh and Julian Crowley from Johns Hopkins, and former graduate student of Pawan, who's in Amsterdam. I'm gonna talk quickly through some of the projects that I have done in TDs. The most interesting ones that I think. The one thing I'm going to talk about first is we predict that all TDs should have bright infrared emission. And also we talk about TDs, they actually support the existence of black hole event horizon. The third project I'm going to talk about is some of TDs, they launch relativistic jets. And we'll talk about the properties of those jets. Here is a picture that when the star, a TD, this is what a TD happens. When a star, shoot it from infinity, getting all the way close to about 1 AU, the distance between the Earth and the Sun, the gravity, the tidal gravity of the supermassive black hole at the center of the galaxy is so strong, the star cannot keep its spherical shape anymore because its self-gravity is not strong enough. So it gets stretched out, it gets compressed in a transverse direction, gets stretched out in this direction, and then half of the mass is ejected because it gains a little bit angular momentum. The other half loses angular momentum, becomes bound orbit, falls back. And then this bound part, half of the bound mass gets accreted onto the black hole. So TDs are mostly found in optical and UV. I'm going to talk about a little bit about the observation over here. So you take a look at a typical TDE. They show very simple spectrum. It's just a thermal spectrum and nothing else in the optical and UV. A thermal spectrum, what you can see is that we don't really know where the peak is. You know that we're on the religion's tail, but the temperature could be higher, and also there could be dust extinction. If for those red dots, I should take this one as an example, those red dots are not extinction corrected. If you correct for some extinction, you can actually get a much higher temperature and much higher luminosity. So we don't know what's the bolometric luminosity of TDs, most of them, but we do know that they are probably in this range, and we know the rate of TDE per galaxy about 10 to the minus 5. So every 100,000 years, there will be a star that falls very close to the black hole and get disrupted. And those things last for like a month, and the total radiation energy radiated is like this. So the first question I asked about TD is, so what does this radiation do if it propagates into the interstellar medium, right? So it turns out this radiation, before our work, people think that this radiation is going to go ionize hydrogen because it's UV, higher than 13.6 eV.
Sorry, I had a very probably hyper naive question. How do you estimate the rate of events?
The rate of events? Oh, because let's say you take a certain area of the sky, because we know all the redshift of all of them. So you take a certain area of the sky, you calculate how many galaxies are there, and what's the rate of discovery within this area. How many galaxies, let's say you have a survey lasted for 3 years. How many did you find, right? You divide by the total number of galaxies within your maximum redshift, the maximum distance. Yeah, it's a kind of a rough estimate. There could be some of them, they could be dust obscured. So we really don't really know in very detail. But let me talk about what this radiation is going to do. People think that it's going to ionize hydrogen. If you take the total radiation, let's say every hydrogen atom takes 13.6 eV to ionize, then you find that it's going to ionize a region of a few parsecs, about 10 light years, about 20 light years, surrounding the supermassive black hole. And you calculate what's the Coulomb density of hydrogen that it's going to ionize. It turns out to be 10 to the 22, which suggests if this gas is dusty, if it is a dust-gas mixture, you find that the dust extinction is 10. So most of the radiation doesn't get to 6 parsec. It only goes to 1/10 of it, and it gets absorbed by dust. So that's what we found, that if this UV radiation goes to a dust-gas mixture, most of the radiation gets absorbed by dust, and the dust gets heated up. There is a characteristic temperature where dust sublimate, according to its the strength of the molecular bonds in dust. And you can calculate what's the characteristic radius where the dust gets sublimated, and then you can make predictions. Those dust will absorb such amount of energy. We take a fraction, which is the sky covering factor. You view it from the black hole and see how much of your sky is covered by dust. This fraction of the total energy is going to get absorbed by dust and re-emitted. in the infrared at this certain wavelength related to the temperature. So you can calculate, oh yeah, it's gonna be about 10 to the 42 erg per second, fairly bright, depending on the distance. The duration of this infrared energies come out from the light crossing time of this dust shell, and then you can predict that, oh, after a TDE occurs, you look at the TDE in the infrared. After let's say a few years, you're gonna see it bright in the infrared, and it turns out at that time we didn't know any we didn't know any infrared facilities, and it turns out those data are already in there. After our paper published, people immediately found, oh, there are like every TDE has this infrared emission. So I'm gonna take one example. This one found by PDF. This telescope is called WISE. So now all the infrared detections are found by WISE because this is a wide field of the infrared, all sky infrared survey. It takes a picture of the entire sky, patch by patch, every like 3 months. So it's really perfect for searching for an infrared emission. So this one has 3.4 micron and 4.6 micron right at the peak. So you can find that for this one it has 3.4 micron detection, but no 4.6 detection, which means the dust temperature is pretty high. It's higher than this wavelength. And then for the other ones, you also get that. And from this duration, it's very interesting. From this duration, you can find where the dust is, how distant is the dust from your supermassive black hole. It's determined by either your sublimation temperature. If the dust is actually farther away than the sublimation temperature, they don't sublimate. So it could be farther. But based on the temperature being so high, this radius corresponds to the sublimation temperature. From this, you can calculate what's the luminosity, UV luminosity of the TDE, which we actually don't know because the peak of the UV spectrum is not observed. So from this, actually, you can calculate for that event, the UV luminosity is this. And then we know how long did optical emission last. Multiplied by the UV luminosity, we get the total energy, radiation energy, which is tended to be this. And from that, you get, this is the total energy in the infrared, divided by the total energy in the optical UV, you get the sky covering factor. So it's a very little dust, like 1% of the sky. So this means this method is very sensitive. So 1% of the sky is covered by dust, could be patchy on the sky, but we can still detect very bright dust emission. This one is from a Euler. Some people know those are dusty galaxies. Right now, the infrared emission is still rising. We don't know where it's going. So with this new infrared window opened, we can study TDE physics, especially the volumetric luminosity, which those are some statistics of TDE luminosity. Those are only optical luminosities. We actually don't know. Those are considered as lower limits. So there should be an upper limit set by this volumetric luminosity. Okay, we can also study dust physics if you guys are interested.
Previous one was 10 to the 45.
Yeah, this one. But the optical luminosity is only
showing optical.
Yeah, it is this one. If so, yeah,
But you can also get a UV for each of these.
no, because the peaks are in a far UV. We don't have any telescope.
Here you got it.
This, yeah, for this one I should have brought it. This is a screen cut from other papers. This actually is here. Oh, it's FH45. It's there. So for this one, but not all of them have infrared detection. Some of them don't. Some of them do. Yeah.
Some of them are just not caught at peak. So they might have the wavelength coverage, but they just didn't happen to catch it exactly at the peak of the flare. Like the assassin events, they caught them on the tail.
Let's say for this assessing this event, some of the assessing event, you actually don't know where the peak is. You can still fit a black body power up. Let's say for this red one, who knows where the peak is? It could be, it's just a new square, a religion's tail. It could be, higher. It could be even higher than there.
Right, but I'm saying the assassin events, they caught them on the tail in terms
Oh,
of time.
sometimes. Yeah,
so
the time.
They could have been
then exactly.
a few times brighter than what these SCDs indicate.
Exactly. So this is the way we can actually tell what is the peak volumetric luminosity. Okay. So this is the first thing that I did. I'm gonna go through quickly. The second thing that I did with Ramesh is there are those supermassive objects at the center of every large galaxies. We know they pull stars and stars orbiting around them. regarding to the nature of those objects, we know they are very compact. You can look at the star with the smallest orbit, and you can get a density estimate. They're very compact. If they are star clusters, they won't be stable. Could be collisions and evaporation of those. And right now with TDEs, think about other galaxies that are causing TDEs that we observe TDEs from. Those galaxies, in order to disrupt the star, whatever it is, the central massive object has to be its density has to be higher than the stellar density. So it's very high. If you consider the effective density of a black hole, they are not much far away from each other. So they have to be very compact. They can't be star clusters. But still, within this compactness, there are many alternative models. They can be very compact as you want, but they can still cause TDEs. The question is there any evidence, direct evidence, for there being an event horizon around those objects? So, searching for the event horizon, we have this event horizon telescope, which has pretty much resolved. The supermassive object at the center of the Milky Way, which is 2 times the source radius, and at the center of M87, they are very close to the apparent event horizon radius. We're going to get a much better data later on. So we want to ask, if they don't have an event horizon, what happens, right? If they don't have an event horizon, let's say they're very exotic objects with a hard surface. And what people have done, including Ramesh on both of those, is that you look at the galactic X-ray binaries. For those neutron star binaries in the quiescent states, their luminosities are much higher than, by 2 orders of magnitude, higher than those black hole binaries in quiescent states. The interpretation is that the neutron stars, they have a hard surface. Matter falling on them, there is emission from the surface. But for black holes, matter just fall in and nothing comes out. So there's no emission from the surface itself. And you can also do the same analysis at, let's say, for a supermassive object at the center of Milky Way or this galaxy M87. You can find that this object is given out a jet luminosity of 10 to the 44 erg. Some matter has to be falling onto this object at this rate or above. But you look at the luminosity coming out from this object, it's much below that. So there is a deficit of any emission from if there is a surface.
But this doesn't depend on what is the surface made of. In the sense that this object, whatever, if there are not black holes, it will be super strange objects, right?
Yeah, they are.
So we don't know.
Exotic.
There is, of course, a window for some weird physics that we don't know, right? So, are you assuming something when you say this?
They have to involve exotic physics. For those black hole alternatives, the physics that we don't know currently. Okay, so what I considered, if you have such a massive object sitting at the center of the galaxy, now you shoot stars towards it. If it is a black hole, the star gets swallowed. Nothing. You see nothing, right? If there is, let's say, a hard surface over there, the star collides onto the surface, and we see what happens, right? If this surface radius is larger than the tidal disruption radius, the star doesn't get disrupted before hitting the surface. So there will be a collision onto the surface, and the star will be shocked. The collision basically happens at the speed of light. The star gets smashed onto the surface, and the shocked gas will enclose the hard surface, which will form an radiation-dominated envelope. And this envelope will radiate at approximately Eddington luminosity, which is super bright for those massive objects.
Yeah, but for instance, you mentioned one example. One of the examples is like boson stars.
Yeah.
So why you say I just imagine a situation in which you don't have like a hard surface, but some profile that eventually leads to some physical process that also prevents this radiation to be seen.
Yes, indeed. Some of the exotic objects, they don't have hard surface either. Let's say for the gravity star or for boson star, they don't have. For a star that actually collides, that actually falls onto those objects. So
you would say in that case, we don't.
Yeah, they can mimic black hole as much as you can. Yeah, there is a parameter. Yeah, exactly. I'll show you the limits that we have very soon. So in terms of when the surface is very compact, you get this, when the star gets actually disrupted, you will have this fallback and accretion disk. But this accretion disk, there will also be matter falling onto the surface and accumulate, form this emitting luminosity from this. We don't consider this because there will be emission from the disk, which we can't distinguish. We only consider those massive objects that we're sure that there will be no disk. There's only this envelope, possibly. And we calculate, this is going to be black body emission. We calculate the temperature for different surface radius. This is the surface radius divided by spatial radius -1. So it's a little bit above, when it's, let's say, 10 to the -4, above the spatial radius, a little bit above it. You can calculate what the temperature will be depending on the mass, and what the G-band luminosity will be, and those can be detected. They're observable for those telescopes, Pan-STARRS and LSST in the future. And so if you take into account those this rate of stars falling onto those objects and integrate over the mass function of all those objects across the universe that we can see, you find that within about 3.5 years that Pan-STARRS was operating in the past, you would expect about 20 such events being discovered. Those events will have flat light curves lasting for a couple of years with the black body temperature, in which the temperature depends on the surface radius. But we have not seen any of those. So we have ruled out any hard surface that's above about 10 to the -4 +1 times the spatial radius. Anything above there, there's nothing there. It's amazing that such a 1.8 meter telescope can do such a job and rule out. In the future, LSST is going to push it by 2 orders of magnitude. Okay, I'm going to go quickly through my last thing very quickly. So this my last thing is about those TDs that actually launch jets. There are 2 TDs that we know they launch jets. The reason being that we have observed very bright X-rays. Those are triggered by swift gamma ray satellite. Then you slew your X-ray telescope towards them, and you find that the X-rays last for more than a year, a couple of years. Those are rest frame days. The luminosities, if you take about a million solar mass black hole, the luminosities are about 1,000 times the energy luminosity. You can't really see the variability from here, but if you zoom in, you see the variability of the light curve about 10 times the gravitational radius. So such a small radius, such a high luminosity coming from such a small compact region, meaning there is something relativistically moving towards us. So we think that there is a relativistic jet from those 2 TDs that are pointing towards the Earth, and that's the story. If you look at the SED, which have radio all the way from UV optical and X-rays, the radios are from the jets interacting with the interstellar medium. There will be an external shock. We don't talk about that. We talk about, so there will be this X-ray powered of the non-thermal X-rays. We are interested in this optical emission, UV optical emission. You can see that for this one, Swift J2058, it has a thermal optical UV emission. For the other one, it has a very strong dust extinction. If you correct that, it's going to bump back. But we really don't know what the dust extinction is. So right now, I'm only working on this one, 2058. If you zoom in to that and plot the spectrum, is really beautiful, the black body. Simply from this plot, you can tell some properties of this black body emitting surface, what it is, where it is, right? So it's if you take one data point on the Rayleigh's tail, you know that its luminosity, this L nil, should be proportional to this and R squared T. We don't know where the temperature is. That's for the same reason we don't have far infrared, we don't have far UV coverage. It can be higher than some lower limit. So, but what we know from this data point is that whatever the temperature is, it must be proportional to the photosphere radius to the -2. We know some lower limit based on this. There is a lower limit of the temperature, so that gets the upper limit of this radius. There is also an upper limit of the bolometric luminosity. You can't extend your temperature so high that the luminosity exceeds your total energy budget of the entire event. So that gives you 10 to the 47 erg per second. You can't like arbitrarily extend it too much. So that gives you a lower limit of those whatever the photosphere is. So there is a very large scale photosphere that is emitting this thermal emission. You can also do the same analysis for other long-jetted TDs. They all turn out to be within this range. So the picture of those jetted TDs are like this. So you have a star that's falling in, getting disrupted, hitting a disk on the size of, let's say, 10 to 100 spatial radius. But that's not what we see. What we see, the UV optical emission is from some large-scale photosphere that's about 1,000 to 10,000 times larger than the gravitational radii. That's what we see. And we are observing there is a relativistic jet pointing towards the observer. What we don't know is where is this gamma ray and the X-rays are, where do they come from? They could be from above the photosphere or below the photosphere. We were debating in 2016, we didn't know what's going on. It turns out there is a new observation that came out that can solve this. That's gonna be the topic that I'm gonna talk about. This new observation came out like a year ago. They did reverberation observation. It's kind of complicated, but it's very simple. If you take two bands, they took XMM Newton X-ray data lasting for about a few times 10 to the 4 seconds, like less than a day at 14 days from the discovery. If you take two bands from 0.3 to 1 keV and the other band 1 to 4 keV, you plot the light curve of the two bands, and then you do cross correlation of the two bands. You can see that within this frequency range, the fluctuation in the softer band lags behind the fluctuation of the high frequency band. Those are called soft lag. And then you take this frequency, and then you beam all the energy to a finer beam. Not those are gross beam. You wanna beam it to finer energy beams, and then you do the same cross correlation, and then you find that at this energy, there is a peak here, which means there are some of the photons at this energy, they are lag behind. Their fluctuation, they're all fluctuating. The light curve at this frequency lag behind, which we call the continuum. There is a line here. The line photons lag behind the continuum by about 100 seconds. And this corresponds to the iron K alpha line, which has been discovered in micro pulsars and other AGNs. This immediately tells you that this jet X-rays are interacting with optically thick gas. So it cannot be the first scenario. And you can also see that those are blue shifted towards us. So there is something that's moving towards us. It cannot be the disk motion, which will be perpendicular to our line of sight. So there must be an outflow that's moving towards us. So this leads to the interpretation by this paper. They say that there must be an outflow, and from the delay time, from the lag time, you can calculate. These photons will lag behind the direct emission from the jet. You can argue that those things are from 10 to the 13 centimeters, and in order to explain the red wing, you need some gravitational redshift. So they say that there are some photons that are actually going towards the black hole, very close to the black hole, and then get reflected. From that, they require that, it's kind of strange that they require that the jet has to be subrelativistic, because at such a large radius, there is no gravitational redshift. You have to have some photons shooting backwards towards the black hole and then get reflected. It turns out this model has like lots of trouble. I'm going to name two of them. So one trouble is if you assume this X-ray source being isotropic, if the X-ray source is not moving relativistic, there's an isotropic Illumina X-ray. You calculate the pressure of the X-rays hitting on the wall. It's much larger than the ambient pressure in the gas. It's basically going to blow the gas away. And you can also calculate at this flux limit, at this X-ray flux hitting on the wall, you can calculate ionization timescale, which is much shorter than the recombination timescale, which means like one atom out of 1,000 will have one electron. There's no way you produce any iron K alpha line out of this. So what's wrong with this? So it turns out they ignored there's one observational fact that those lag time is diluted. So it's very simple to explain what dilution is. So if you take the light curve at this band, let's say 7 to 8 keV band, you take the light curve, it has two components. One is the continuing components, which is, let's say, sinusoidal. There is another component, which is the line component, the K alpha line component, which has a lower amplitude, which is much lower. I'll show you later on. The Q is much smaller than 1, but it's delayed by some true delay time, and then you add them up. It's very easy to do the mathematical. It's like you can calculate what A and B is, and then you do cross correlation of those two functions. You find that the lag time is B times the true lag time. When the amplitude ratio of the line and the continuum is small, it turns out B equals to Q times the sinc function of this. This turns out to be much smaller than 1, so this is 1. So B is on the order of this amplitude ratio. So it turns out the observed lag time is much smaller than the true lag time.
Are you going to wrap up soon?
Very soon, yeah. So we calculated. So we add that up. We calculated if you have if you take into account the lag time being longer, you can actually allow the X-rays at 10 times larger radius, being produced at 10 times larger radius. We also calculated, let's say, for a relativistic jet, the intensity will depend on the angle. You do the integration along the funnel wall and calculate the yield of K alpha lines. You can calculate what's the equivalent width, and then you get the true lag time from that, basically. What we predict is that these X-rays are hitting on the wall. This momentum parallel to the wall is gonna drive an outflow from this simple argument. So our new picture is like this. So you have this very large scale thermal photosphere, and the X-rays are produced below this photosphere, and X-rays are hitting on the wall and drive an outflow that's moving out at about 0.3 C. This corresponds to the blue shift of the line. So, and also, we also calculated what's the reprocessed energy. You take the beaming corrected total X-ray energy, how much of a fraction of that gets reprocessed, and that actually gives a UV luminosity. This outflow will interact with the ISM producing radio, which also agrees with the radio with the radio band. So that's gonna be my summary. I hope I convinced you that we have a more complete picture of JTTDs and we have done that. Thank you so much for your attention.
We have time for 1 or 2 quick questions. Ramesh?
So Wenbin, for a few objects, you seem to be able to come up with some estimate of UV luminosity.
Yes, exactly.
And it looks like 10 to the 45 units per second, right?
For that one, there is another one which is 10 to the 44, which is normal.
Okay.
There are some normal ones, but there are some brighter
Yeah,
ones.
so the 10 to the 45, and if those typical black hole masses are 10 to the 6,
Yeah, 1,000,000 or 3 times that.
3 times.
Yeah,
So these are definitely super Eddington.
exactly. For
Like,
sure.
would it be 10 times Eddington?
10 times or 10 times, I would say, on the order of 10 times.
Okay, now, is there any correlation between that kind of super Eddington luminosity and presence of jets? Are the jet, I mean, this one jet source
Yeah,
is super Eddington.
there are a couple of TDs that the bolometric luminosity is, let's say, 10 times the Eddington luminosity, but they don't have jets.
They don't have jets.
Yeah, but for this jetted one, it is super Eddington in the UV. Yeah.
Okay.
So you could say there could be, but there are exceptions.
But you're saying there are also objects that are not super Eddington.
Not super Eddington.
Can you prove that,
Prove-
or is it only?
Yeah, there are objects. If they are not super Eddington, they don't have jets. But that's what.
No, but the question is a slightly different one. Are there objects? And the answer is there are probably objects which are sub-Eddington.
There are.
Yes.
Where
Lower luminosity.
you know
kind of-
enough information
No,
have that
no,
you know
not
that.
No,
with great confidence.
right now
Huh?
there is marginal Eddington one probably. Something like that. Yeah. No sub Eddington ones.
We should talk.
Okay. Let's continue the discussion at 4:30 over pizza. Our speaker, guys.
Thank you.